I'm Zhang Dingyan from IPAS at Shanghai Jiao University. You can call me DY in the Q&A session and the whole conference. I would like to share our insights and system solutions for optimizing KVCache management subsystem in LLM serving. This is a joint work with Alibaba Tong lab. Nowadays, LLMs are key service on the cloud, and KVCache is a key technique to support serving. Specifically, KVCache is the intermediate computation result used throughout multi-step generations. When serving individual requests, computing them requires huge computation power. Fortunately, LLMs have a nice property. Requests with the same prefix of inputs share the same KVCache. Therefore, by caching requests KVCache in a caching system, which we term as KVCache cache, upon hits, in this example, this is a bad day shares the same prefix as this is a good day. We can skip most of the computations and thus save huge GPU cycles. Such a KVCache cache is not only beneficial to request latency, but also beneficial to the overall system throughput because precious GPU cycles can be saved from redundant computation. There are two key design sub-goals for a KVCache cache system for a cloud vendor: high cache hit rate and low cache cost. To achieve such goals, we need to answer two questions. The first is which requests to cache and which to evict. This is a fundamental problem in any caching system, but more challenging for LLMs because not all in-cache KVCache blocks can get hit easily due to the LLM's nature. Only requests with shared prefix contribute to these hits. As shown in the diagram, suppose this is a good day, it's processed and cached, then come additional two requests, resulting in a partial miss and a total miss. The KVCache of good and day is not hit. Achieving a high hit rate requires identifying such KVCache blocks and evicting them if necessary. The second question to answer is that how much cache space is required for KVCache? Answering this question is also important because it is critical to the cost of deploying an LLM service. Achieving low cost is also challenging for KVCache cache subsystem because since GPU computes really fast, the KVCache needs to be placed at a high-speed memory medium like DRAM, including both the GPU HBM and RDMA accessible remote host memory. Unfortunately, such an upper-tier memory medium are notoriously small and precious on the cloud. Given that the total KVCache of all users is large, how to provision the appropriate memory capacity to balance the performance and cost is also an important design goal. While existing systems try to build an LLM caching system using traditional designs like LRU, we found that they all fall short because KVCache hits enjoy diverse temporal localities that could make a general-purpose design ineffective. Specifically, the variability stems from three factors. The first is LLM requests have terms. As shown in the diagram, when we query an LLM, the LLM gives a response. If that response is not satisfactory, we will start another query. Because the LLM is not aware of the conversation context, cloud vendors will put the previous requests and responses as the prefix of the new requests. We term them the context. This request is called the second term request. The user could start multiple terms if they think it's necessary. Well, we can see that a multi-term request naturally shares the prefix of a previous term. The probability of starting a next term is different. Ignoring such a probability may leave a large but unused multi-term request in the KVCache cache, causing degraded cache hit as well as increased cost due to the waste of memory. Besides, LLM requests are multimodal, including pure text interaction or image and acoustic understanding. These requests have different reaction patterns due to the fact that our brain uses different regions to process different modality. Since the cache reuse is dependent on how requests will be reused, these diverse modalities also make the cache reuse vary, which we argue that a KVCache system within an LLM serving backend needs to consider. Finally, LLM requests can be issued by both humans and computer programs. We call them nowadays as agents. As we can imagine, the programs have a much swifter reaction time and execution pattern than human beings. And such a fact should also influence the design choice of an efficient KVCache system. Existing systems, as we mentioned, all adopt a workload-agnostic approach, which we found inefficient. For example, a general-purpose LRU, LFU, or FIFO cache eviction policy, which we found could lead to up to 24% more misses than a workload-aware approach that we will describe later, especially under limited KVCache capacity. While one possible solution is to provision sufficient memory to mitigate cache miss issue. For example, Mooncake leverages all the available DRAM in a cluster for caching. Nonetheless, our study shows that such a solution would waste up to 40% of the cluster's DRAM because not so many requests need to be cached. Since the KVCache reuse is ephemeral, we will discuss this point later. To systematically design an efficient KVCache system, it is answering those two vital questions. We argue that we need to take a workload-driven approach in a two-step manner. First, we need to characterize the KVCache reuse patterns of different LLM workloads. Second, based on the insights and findings of the characterization, we propose workload-aware system designs. Specifically, our characterization is conducted as follows. First, we categorize requests with the same signature as workload. Second, we characterize the reuse pattern of each workload. Based on these patterns of workloads, we further propose a workload-aware KVCache eviction policy to retain KVCaches that are likely to contribute more hits. And we propose a workload-aware KVCache space estimator to accurately provision the cache space for each workload and thus minimize the cost of deploying the KVCache system. Before moving on, we found analyzing KVCache reuse patterns for real-world LLM requests is challenging. This is because we need an in-depth analysis of the serving requests. As shown in the diagram, to categorize different requests as workloads, the type information is indispensable. It is whether it's invoked by human or an agent, whether it's text-only or multimodal. The number of turns is also of great significance, as we mentioned before. Moreover, to analyze the reuse pattern of requests, timestamp of each request must be present for sure. That is, we need to know when the request is served by the system. Don't forget the hashes of KVCache block within each request. We need them to identify hits and misses due to the prefix sharing nature of LLMs. After scanning all available open source traces as far as we know, we found they all miss important information. To this end, we conducted a comprehensive and systematic study on a one-week anonymous trace from Alibaba, one of the leading LLM service provider, for which we collected traces containing all the necessary information. Based on the collected trace, we conducted our KVCache reuse pattern characterization and proposed our system designs. Our traces are also open sourced to benefit the broad research community. Below is the outline of the remaining talk. First, we start with the key insights and takeaways unknown to the most of the research community. We argue our findings could benefit the design of KVCache systems. Our first insight is that the use pattern of workload differs. Here, we define the signature of a workload as the product of its type and turn. For example, a text and a multimodal request are two workloads clearly, while a single-turn chatbot request and a double-turn request also belong to different workloads. Based on our taxonomy, we can see a distinguishable reuse time distribution from different workloads. This is shown in the CDF. An interesting discovery is that single-turn requests also contribute a lot of cache hits. This gives an important takeaway. Caching and eviction should consider workload categories, including the single-turn requests. While the previous insight indicates that we need to differentiate the reuse pattern of different workloads, it does not tell us how to make it. Another important insight we draw is that given a time period, it is 1 hour in a day, the reuse probability of a workload follows approximately an exponential distribution. More importantly, the distribution across consecutive hours seems stationary, as shown in the figure. A density function in red and another in blue are overlapped, as we can only see the shape of distribution in purple. More interestingly, this stationary property is also applicable to the same period across days. The density function of day 1 and day 2 are in the same shape either. This suggests that we can profile the historical usage patterns and derive the current KVCache policies of a KVCache cache system. Our third insight is that most KVCache reuses are ephemeral. Here, the lifespan means how long a KVCache block needs to be retained in order to facilitate future reuse. Specifically, in trace A, 90% KVCache are never reused after 10 minutes, and the number is even 0.3 seconds in trace B. This suggests that we may not need a very large KVCache cache space for LLM serving. In addition, the short lifespan indicates that a frequency-based policy like LFU is not optimal because a dead KVCache would not get evicted, though due to a high reuse frequency. More interestingly, we found that the lifespan of KVCache of a workload is also predictable. Look at the figure. We slice a day into 10-minute time intervals, and the color intensity indicates that the length of lifespan. It seems that the lifespan is changing over the day, as shown by these speckles. However, once zooming out, we can see that color remains uniform at each row, which means reuse time is quite predictable given different hours in a day. To draw a conclusion, these insights encourage us to profile the history and predict the KVCache space usage for LLM serving. We have many interesting findings in our paper, but due to time issues, we only talk 3 of them right now. Now we can answer the question of how large KVCache space is needed with aforementioned insight 3. Then arises another important question, how to leverage our insights to improve the KVCache system design. Let's take cache eviction policy as an example. Specifically, a KVCache policy decides which KVCache block to evict once we have insufficient space for caching. Essentially, KVCache policy design can be reduced to a problem of eviction priority calculation. For example, in the famous list recently used policy LRU, eviction priority is defined as minus T last. T minus T last is the recently used, and the leading minus indicates the least. However, as we can see, it ignores the predictability of the reuse probability based on our characterization. Therefore, leveraging our first 2 insights that different workloads have predictable reuse probability, we can first use the historical information to fit an exponential distribution to each of the workload, and then use the time in the cache to estimate the probability of future reuses. As a result, we can select those KVCache with lower future reuse probability when evicting. One problem of using this distribution for an estimation is that it assumes that a KVCache will be eventually reused, which is not true due to the ephemeral reuse pattern of KVCache based on our insight 3. Thus, we further regulate our policies to consider this feature by only considering a short time window in the distribution, where the estimated time window, we call it life, is determined via profiling. There are more details for our cache policy design, but due to the time reasons, we will only sketch the main rationale here. We can see that under real-world traces collected by us, our workload-aware policy can improve the KVCache hit rate of VLLM by 1 to 24% compared to its current workload-agnostic policies. This optimized policy further brings up to 42% skewed TTFT time reduction for the end-to-end system serving. There are many more detailed policies and evaluations in our paper. Besides, we also have some more interesting discoveries. Please check our paper if interested. In conclusion, in this work, we argue that we need to first characterize the features of serving workloads before we optimize the components of serving systems. And a workload-driven approach suits well to KVCache cache subsystem, given the variability of requests. Now, thank you for your attention, and we will enter the question section.